Okay, hello Precalc C. Turn this on too. Check and make sure that's okay. Sure. Welcome. Got a brand new whiteboard, using it for the first time ever right now, and it looks beautiful and it's very large, and I just hope it erases well. We will see. This is me now going over the sequences and series packet. I meant to make this video a long time ago. We previously did pages 1 through 8, and then last week, early last week, you did pages 9 through 11, and then page 12. So okay, let's go. There's a whole bunch of interesting problems here. We're on number 33, and this page is all about complex numbers, it seems. So there's a geometric sequence of complex numbers. The first term is I, and the common ratio is 2I. Okay, so it must be that the first term is I. If we're multiplying by 2I every time, then 2I times I is 2I squared, so it's going to be negative 2. If I multiply by 2I again, then that's going to be negative 4I. If I multiply by 2I again, then I will get, again, I squared, so that'll be negative 8, so that'll be 8, etc. Okay, I think it's specifically asked for the first 5 terms. So, okay, ooh, that seems to erase pretty well. If I multiply by 2I again, I get 16I, etc. And now the question is, find the sum of the first 5 terms. Okay, the simplest thing to do would be to just add these 5 numbers up, but let's not do it that way. Let's use the formula. The formula for the sum of the first n terms of a geometric series is a times 1 minus r to the n over 1 minus r. So here, if I'm summing up the first 5 terms, well, then that's going to be the first term times 1 minus r, we already agreed was 2I. That's what I'm multiplying by every time, right? Yeah. 2I, so that to the 5th, all over 1 minus 2I. Alright, so this is one of those problems where, I guess you could sort of stop almost at any point, but I think it's nice to do some simplification here. So let's see, what do we have? Well, what is 2I to the 5th? So I get I times 1 minus. 2I to the 5th would be, 2 to the 5th is 32, and I to the 5th is just like I. So this becomes minus 32I over 1 minus 2I. But, okay, that can also be simplified a little bit, because, let's see, if I distribute that I through, I get I minus 32I squared, which becomes 32 minus I over 1 minus 2I. So this is looking a little bit better, and okay, you kind of want to give your answer in standard complex number form, a plus bi. So if I multiply by 1 minus plus 2I over 1 plus 2I, in other words, multiplying by the conjugate, then, okay, let's see, what do we get? On the top we get 32, well, maybe I'll just write it out, 32 plus 64I minus I, but minus 2I squared, so it's another plus 2, over 1 minus 2I times 1 plus 2I is 1 minus 4I squared, so that's 1 plus 4, so that's 5. So in fact, man, I hope I'm doing this right, this gives me 34 plus, it seems like a strange number. Did I do something wrong? I hope not. Dun, 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 dun. I plus, let's see, did I mess this up? What mess it? Okay, let me just try that again. 32 plus 64I minus I, and then that's minus, yeah, this looks right. 34, 1 plus 2I. My paper says something different. I must be right. I plus, oh, I just made a stupid mistake right here. That's just plus I. So it's just I minus 32i squared, so I plus 32. Okay, so that was just, I don't know where that came from. Anyway, so multiplying through, I get 32 plus 64i plus I plus 2i squared, so it's plus 2. Okay, so what do we get? In fact, this is then minus 2, and that's why this number works out kind of nicely, because this becomes 30 plus 65i over 5, and the answer is then 6 plus 13i. Is that right? Yeah, 6 plus 13i, yeah. Okay, so, alright, there's nothing really much going on cool in this problem. It's just the fact that, complex numbers are numbers, and you can apply all these techniques of finding the sums if the complex numbers are in a geometric series. Okay, good. Let's go on to the next problem. The next problem is kind of like one big problem. And actually, it's sort of two problems now. So there's 34 and 35. I got all these problems from a textbook. I might have considered writing this out a little bit differently, but anyway, I'll just do what is on the page. We have 1 plus I over 2 plus I squared over 4 plus I cubed over 8 plus I to the 4th over 16, etc. Okay, well, if you give it to me like that, then I know exactly what to do. This is going to be obviously geometric. What am I multiplying by? I'm multiplying by I over 2, by I over 2, etc., by I over 2. Okay, so this is geometric, and what am I trying to do? I'm trying to find the formula for the infinite sum. So, okay, well, if r is I over 2, and I want to find the sum out forever, then I can just use the formula that S is A over 1 minus R. So in fact, let's see, what do we get? We get A, which is 1, over 1 minus I over 2. And let's just simplify this a little bit because I can. That's going to be 2 minus I in the denominator, and when you multiply top and bottom by 2, so I got a common denominator, and I'm also flipping that up. Then I can multiply by 2 plus I over 2 plus I to simplify that denominator a little bit. Anyway, I get 4 minus I squared, so that's 5. So I get 5 in the denominator, and in the top I get 4 plus 2i. Okay, so in standard form, this is 4/5 plus 2/5 I. That's my answer to this part A. And over here in part B, we're given a different problem, which is just 27 minus 9i plus 3i squared minus I cubed, etc. So here I seem to be, what am I doing? I'm dividing by 3 and also multiplying by negative I each time. So this is negative I over 3. Let's just confirm that. Yeah, that's just right. And then if I multiply by negative I over 3 again, let's just confirm that boom, boom, negative cancels, I squared, so that becomes, yeah, plus, no. Is that right? Negative 9i plus 3i. Oh yeah, sure. Because 3i squared is really just negative 3. Well, okay, sure. I'm just multiplying by negative and that, okay. Alright, actually, so sort of not simplifying this I squared into negative 3 is supposedly going to make it sort of easier for me to see that that is the common ratio. Okay, what am I doing? Well, alright, yeah, once again, I'm just adding up the infinite number of terms. So it's going to be the first term, 27 over 1 minus negative I over 3. This is kind of not that exciting of a problem. What am I going to do? This is 27 over 3 plus I over 3. Getting a common denominator, so really that's like 81 over 3 plus I. And if I multiply by 3 minus I over 3 minus I, then I get something in the denominator. I get 9 minus I squared, so that's 10. And in the top, I guess I just get like 243 minus 81i. So I think, is that just this whole problem? Yeah, it just is. So this is 243 over 10 minus 81 over 10i. Okay, so, man, I have so much board space. It's amazing. So that's 34. Now we get to 35, which all of this was basically, I mean, this was kind of, these were basically stupid problems, I'm going to be honest with you. But 35 is not a stupid problem. 35 is like a great problem. It's actually quite cool and very, very interesting. So here is what the situation is. There's this bug. And this bug is crawling. And this bug is crawling in a very particular way. The bug is crawling. So let's just read exactly what it says. The bug travels, starting from the origin, 1 unit east. And so we're going sort of over 1. So that's 1. Stopping at the point, 1 comma 0. And then the bug goes half a unit north. So that looks like about a half, maybe. Won't. And now we're at the point 1 comma 1/2. And then the bug goes 1/4 of a unit west. So, okay, this is sort of hard to do accurately, but now maybe like something like that or whatever. So now, where do we end up? Well, I guess I'm at like 3/4, comma 1/4? No, sorry, 3/4, comma 1/2 still. And then 1/8 units south. So okay, this is now getting kind of complicated, maybe. Well, maybe not. What's happening now if I'm going south? The x-coordinate's going to stay the same. It's still going to be 3/4. But now I'm going down by 1/8, so that's going to be 3/8, I guess. Losing 1/8 off of 4/8, yeah, something like that. Okay, and so what this bug is doing is it's continuing to go kind of like east, north, west, south, east, north, west, south, east, north, west, south. But each time that it turns and goes in a different direction, the magnitude decreases by a factor of 2. And it appears, just from a kind of basic kind of understanding of generally, what the gist is, it appears that we're going to kind of converge at some particular point somewhere. And the question of this problem is, the first question is, find the point where the bug ends up. So after performing this infinite number of moves, where, at what place in the plane does the bug sort of land finally? Okay, well, what we're kind of doing here is adding up an infinite number of vectors. This is one way of thinking about it. So what is this first vector? Well, it's the vector 1, 0, and then we add to that vector 1, 0 the vector 0, comma 1/2. And we add, so that means going up. And then we add the vector negative 1/4, comma 0, because we go 1/4 west. And then we want to add the vector which goes down 1/8, etc. So this is kind of like what's going on here, right? What we're sort of thinking about what's happening here is that we have these sort of individual kind of vectors saying, go 1 unit east, go a half a unit north, go 1/4 of a unit west, go 1/8 of a unit south. So now I'm thinking of north as being positive, south as being negative, just kind of like the map, and east is being positive and west is being negative. And so what we want to do is we want to kind of add up an infinite number of vectors, because after all, the final location of the bug is can be thought of as kind of the sum of the infinite number of these vectors. And if you cut it off at any point, right, if you just add, if you just add these first 4 vectors, then you actually just do end up with 3/4, comma 3/8, assuming I did that correctly, and I think that I did, yeah. Okay, well, complex numbers to the rescue is the answer. vectors really just are complex numbers. This is one of the most useful moments in this whole class that we are going to sort of take advantage of our understanding of complex numbers. And the idea is, and it says it right here on the packet, think of this vector 1, 0, not as the vector, but as a sort of complex number in the complex plane, which is itself fundamentally kind of two-dimensional. So let this be the real axis, let this be the imaginary axis, and so what we're really adding here is just like, this is just 1. And, well, what is this? Well, a vector saying, go up a half, it's kind of like just adding, I over 2. Then, what are we doing? Well, then, we are going to subtract, what's the next thing I do? I go a fourth left. So that's like just subtracting a fourth. And then here, what are we doing? We are going down an eighth. So that's like subtracting I over 8. Okay, and so I basically convert this problem of adding an infinite number of vectors to adding an infinite number of complex numbers. And it's not too surprising to find that this sequence is actually just geometric. What are we doing? Here we are multiplying by I over 2. Here we are again multiplying by I over 2 because I squared is negative. So you have to sort of observe that this is geometric. Actually, there's a kind of a pretty big hint on the packet. Here, if you multiply by I over 2 again, you get this. And so in fact, in disguise, this is just 34a. 34a was meant to actually kind of have already done this problem for you. After all, if you simplify here, these were written in a sort of unsimplified form, but you get 1, you get I over 2, what's I squared over 4, that's negative a fourth, I cubed over 8 is negative I over 8, etc. Okay, and so we already did the work. What happens when you add 1 plus a half plus negative a fourth plus negative 8, etc.? The answer is you get the complex number 4/5 plus 2/5 I. In other words, I think it just says it right there on the packet. Use the formula for the sum of an infinite geometric series to show that that if you add up these infinite number of complex numbers, then via the formula for the sum of an infinite geometric series, we get 4/5 plus 2/5. And so that kind of solves this mysterious vector problem. The answer is, if you add up this infinite number of vectors, you actually just land at the point 4/5 comma 2/5, and that appears very closely to be, the right answer, and just is the right answer. This right here is the vector 4/5 comma 2/5, and so the point 4/5 comma 2/5 is just the final destination of the bug. Okay, and then the follow-up question: how far does the bug travel? How far does the bug travel? Well, now we're not asking anymore for like the displacement of the bug. We don't want to add up the vectors in a way in which we sort of cancel them out when we're going sort of east and then west and east and then west and back and forth again. We're really calculating the sort of displacements. But now I'm just saying, well, what's the distance? What's just the total distance traveled? Well, okay, come on. The bug goes 1, then the bug goes a half, then the bug goes a fourth, then the bug goes an eighth. And so the total distance traveled by the bug is just going to be the sum of this infinite geometric series, and we know that this is just 2. Okay, so since this bug's paths are becoming shorter by a factor of 2 each time, then the bug actually just travels and it makes an infinite number of turns, but only covers a total distance of 2 units, and ends up at the point 4/5 comma 2/5. Okay, good. We're gonna go on to the next page. I'm gonna erase this board now. It's either gonna be wonderful or terrible. Let's see what happens. Wow. This has just like changed my entire life. I am so happy right now. I have made hundreds of hours of videos since April 1st of last year, and now here I am finally with this high quality board. Oh my gosh. Okay. Good, that was page 9. Page 10 is kind of just a cool problem. This is the Tower of Hanoi problem. This is a puzzle. And, okay, here we go. This particular version in the packet says that there are 8 disks of diminishing size from top to bottom, but you can do it with any number, 3, 4, 5, 6, 7, 8. And, yeah. Okay, so the task is to transfer all 8 disks from post A to one of the other 2 posts. Given that, only one disk can be moved at a time, no disk can be placed on top of a smaller disk. Okay, so maybe you've heard of this before. It's kind of a famous problem. I think you even used to maybe program it in 10th grade computer science. I'm not really sure. Let's just kind of do this puzzle really quick. Maybe for one of these things. Let's do it for the case where n is 3. All right, so this is going to involve a little bit of drawing. Let's see, do I want to do that? Well, okay, too late. I guess I've committed myself to it. There's also a animation happening on the class homepage. So let's see if I can do this. I happen to know in advance that this takes 7 steps. So 4, 5. I'm gonna run out of room. 6, 7. Okay. Boom, 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 boom. Okay. So we need to move all 3 of these, whatever, dowels, what's the word they use here? A block of wood. We have to move these 3 blocks of wood. They're just cylinders, sitting on a spoke. We need to move these cylinders from here to here. Okay, but we can only move 1 block at a time, and you can never put a bigger thing on a smaller thing. And so, okay, the idea is, well, I need to get this big block over here, right? But how am I going to do that? Well, it's gonna, at the moment that I move this big block here, there can't be anything there, and the big block will be here, and there can't be anything on top of it, because you can only grab sort of the thing on top. Therefore, I should try to move these 2 little ones to the middle, to clear up some space. So to move the two little ones to the middle, that means I should move the little one here. Okay, so if you followed that, cool. If not, whatever. The point is, you move the little one here. Then, in the next step, you move the medium one here. Then, in the next step, you move the little one on top of the medium one, like that. This is all kind of, so it's like bump, and then bump, and then bump. And then, finally now, I can move that big one over here to its kind of final destination. And then, now, I need to move those 2 both onto here. But before I can do that, I need to first get that little one out of the way. So, like this, and like this. And then, I guess it's more than 7. Oh, it takes 7 moves. Okay, so, I needed 8 pictures. Because now I move the medium one on here, and finally, okay, bad spacing, but good explanation. Hopefully, I do this. So, okay, so I win, and it took me, like I said, it took me 1, 2, 3, 4, 5, 6, 7 moves. Okay, hopefully that kind of makes sense, and also sort of, okay, so the very first question says, let m sub n represent the minimum number of moves needed to move n disks from post A to one of the other posts. Okay, so here I'm just assuming that by default we're always moving it all the way over to the rightmost edge, but if you moved them to the middle, it doesn't really matter. Usually people just move it all the way to the right. Okay, so what have we seen? Well, I guess this was the case with n equals 3. If n equals 2, it's just quite silly, I think, because now, boom, 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 boom. If n equals 2, then I guess it's just even easier, because you have a medium one and a small one, and that's all there is. So I just move the small one here, then move the medium one here, and then put the small one here. So, and if it's if n is just 1, then you just move it. Okay, so using this notation, m1 is 1, m2 we've just seen by kind of brute force is 3, and 3 is 7. And working through these 3 cases is supposed to convince you, or it's supposed to give you some idea about the recursive rule. And so now we're gonna prove the recursive rule. What does it say? Well, it says, suppose you know how to move n-1 disks from post A to another post, and that to do so requires mn-1 moves. Oh, it just gives it away. It just says explain why m sub n is just 2 m sub n minus 1 plus 1. Okay, instead of answering this kind of I don't like the way this packet is telling you to do this, but anyway, point is, suppose you have the case n equals 4. Okay, well if I want to know n equals 4, what am I doing? I am going to have this kind of situation. I have my 3 spokes. Now I have a sort of big, medium, small, tiny. Maybe I'll call it something like that. Okay, and I need to move all 4 of these over here. Well, here's how I should think about this. I should think about this as a 3-step process. In step 1, I move this entire 3 guys from there to the middle. Chop, chop, chop. So here's the kind of big one, and then now the medium, small, and tiny are there. So that's kind of like step 1. Then in step 2, I move this, so boom, boom, boom. In step 2, I move the big one. And then in step 3, I once again move this entire, so here this entire thing went here, and now this entire thing is going to go on top. And then we're done. Okay, I think I'm going kind of way too slow here. The point is that how many total steps does it take in the case n equals 4? Well, however many it takes to move 3 blocks, which I already concluded was 7, then it's going to take me 7 steps to get these 3 onto another one of the 2 spokes. I guess that's why the problem stated it that way. Because there was nothing, there's nothing special about moving here to this 3rd spot. We could just as well have moved to the 2nd spot. So it's going to take me 7 steps to move these 3 here. Then it's going to take me 1 step to move the one all the way in the bottom over to where it needs to be. And then it's going to take me 7 steps to move back again. So I am very confident that mn is actually just going to be, m4 rather, is just going to be m3 plus 1 plus another m3. And in other words, move the 3 blocks to the middle, move the 1 big block over to where it needs to be, move the 3 blocks back again. And similarly, so therefore what is m4? Well, if that's 7, then it's going to be this m4 is going to be 15. And so more generally, anytime now, I think I understand this problem, right? If I want to move n of these blocks, then what do? I first suppose that I know how many steps it takes to move n minus 1 of them. So I move them from the top to the middle, leaving the big block on the bottom. Then I move that big block from the left all the way to the right, and then I move all the n minus 1 blocks back again, and by definition m sub n minus 1 is the number of steps it takes to move n minus 1 blocks. Okay, and so what I've now just done is I've just proven this recursive rule, which the problem just tells you on the packet. Okay, So, what am I doing? Oh yeah. So, okay, great. Then it says just use your answer to part B to check your values for M2 and M3. Oh, notice that, the great thing about having a recursive rule now is that you can just kind of crank them out. And by the way, you double this number and add 1, that gives you the correct answer for M2. Double the number, add 1, that gives you the correct answer for M3. And so, this part is maybe kind of silly, but what is M4? It's 15. What is M5? You double it and add 1, so it's 31. What is M6? You double it and add 1. So that's 63, and I don't remember how far out they wanted me to go. M7, M8, that's kind of crazy, too much numbers. M7 is, what am I doing? 128, so 127, I guess. And M8 would be 255. Okay, and now, does the problem say find an explicit formula for M sub n? Yeah, so I think here it's just pretty clear that the explicit formula is going to be 2 to the n minus 1. You could prove that this is true, I guess kind of by induction or something. Well, I mean, you don't even need to, right? Because if each of these is, well, I'll just leave it at that. Okay, great. And then there's this kind of like silly thing on the bottom that according to some legend, that if you have, at the beginning of time, someone started playing this game with, 64 of these cylinders and doing 1 per second. Is that right? Hold on. Blah, 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 blah. Yeah, 1 per second. Okay, so how long is it going to take? Well, I calculated that it's going to take about 585 billion years, because it's going to take 2 to the 64 minus 1 seconds, and 2 to the 64 minus 1 seconds is about 585 billion years. Okay, so that's pretty exciting. Okay, I'm going to do the next 2 pages in a second. Okay, welcome back. It's the next morning. Here we go to do pages 11 and 12. So, good. Number 37 is a kind of interesting problem. It says, the sum of the first n terms of an arithmetic sequence is given by, and there is this formula. Okay, so we're told in advance that this is an arithmetic sequence. So that's extremely helpful. And we're given an explicit formula for the sum of the first n terms of this arithmetic sequence. And so, here it is. S sub n is n squared plus 4n. So this is a little bit of an interesting problem, because you're not given the first term of the sequence or the common difference or anything else, but you are given a formula which will tell you what the sum of the first n terms is, and you're told that it's arithmetic. Okay, well, the fast, really fast kind of 1-minute way to do this problem is to just plug in some numbers. So if this is the formula which will tell me for any n what the sum of the first n terms is, then, okay, well, what's the sum of the first 1 terms? Well, if you just simply plug 1 in here, you get, 1 plus 4 is 5. So if the sum of the first 1 terms of this sequence is 5, then it means that the first term of the sequence is just 5. And if you ask for if you plug in 2 into this formula, then it's going to just spit out the sum of the first 2 terms. So if you plug in 2, you get 8, you plug in 2, you get 2 squared 4, yeah, 8. So, if the sum of the first, is that right? What have I done? N squared plus 4n. If I plug in 2 squared is 4 plus 8, which is 12. Yeah, I knew that was wrong. Anyway, good. 4 plus 8 is 12. Yeah, so if the sum of the first 2 terms is 12, well, if the first term is 5, and the sum of the first 2 terms is 12, then I must have just added 7 to get from the first term to the next term. And so the second term of this sequence is 7. And you can just stop there. We're done with this problem, because once you tell me that it is arithmetic, and once I know that the first term is 5, and once I know that the second term is 7, then I must be going up by 2, and that's actually it, right? What were we supposed to find? Find the first term and the common difference. Done. The first term is 5, and the common difference is 2. Alright, this problem might be a little bit bewildering. You have to sort of think to do that, and then once you're done, maybe you stop thinking. But we can think about this a little bit more, because what's really going on here is we have this, is kind of interesting, because what we have here is this sort of partial sum, and well, what is this partial sum? It's actually just like n times n plus 4, I guess. Yeah. And so we can look at the value of this partial sum for various values of n. So I guess I should start with, let's just do 1, 2, 3, 4, 5. That seems like good enough. Let's see, can I do this quickly? 1 n times n plus 4. Yeah, so right, so that's 1 times 5, so that's 5, 2 times 6, so that's 12, 3 times 7, so that's 21, 4 times 8, so that's 32, and 5 times 9, so that's 45. Okay, so I'm actually now making a chart of S sub n. What is S sub n? It's the nth partial sum. There's a whole lot of stuff going on here. You can just kind of invent calculus sort of on the spot by looking at little patterns like this. On the one hand, this is just kind of a generic quadratic. On the other hand, this column represents the sum of the terms so far. And if you take the difference between the sum of the first 2 terms and the sum of the first 1 terms, then you're going to get the sort of second term. I guess I should have started with 0. That would have been a little bit better. Hold on, I'm going to squeeze that in, I realize now. So this, putting 0 in here is actually a good idea, because then this formula, this is n, this is n plus 4, this formula then yields, well, it just yields 0. So the sum of the first 0 terms is 0. That sounds like a silly thing to write, but then I do want to kind of I'm looking at the gaps. So the gap between the sum of the of no terms and the sum of the first 1 terms is 5, which is to say that the first term is 5. And the gap between the sum of the first 3 terms and the sum of the first 2 terms is just the third term. And so this is kind of a different way of thinking about this table. If your sequence is arithmetic, another way of saying that is that it's just a linear function. It's a linear function because the slope, the change, is constant, because with each increase by 1 in the input, the output goes up by a certain constant. And it must, because the constant by which it goes up is just the common difference. So if you think about just on some sort of deep level, what is an arithmetic sequence? An arithmetic sequence is just a linear function. It's going to be a sequence will be arithmetic if, as we've seen, the formula, the generic formula for the nth term of the sequence is the first term plus n minus 1d. Okay, and perhaps we do a disservice by not sort of focusing on the kind of analogy between this and the study of linear functions in Algebra 1. After all, if you were to graph something we've literally never done, this sequence or something like that, then what sort of is this, right? This is kind of like the y, so the output. What is the value of the nth term? Well, here, the input, writing it in a more standard form, would be d, the constant, times n, and then, plus something else, which would be a1 minus d. So maybe I don't want to write y here because that's kind of wrong. But focusing on this kind of pattern, we see that here the variable is n. The first term is a constant. D is a constant. What is d? In fact, it's just the slope. So this has a superficial kind of y equals mx plus b kind of format to it. And in this case, the slope, the amount by which the output increases for some increase by 1 in the input is just the common difference. Okay, so what am I trying to say? I'm trying to say, look, every arithmetic sequence is in fact just a sequence whose explicit formula is a linear function, and therefore the sum of the terms of a linear function are going to be a quadratic function. And it's not a coincidence that the formula for the sum of the first n terms in an arithmetic sequence, which is n over 2 times 2 a sub 1 plus n minus 1d, writing it like this might kind of maybe obscure what's going on, because what we really have here is, well, I don't want to write this out because I'm spending too much time on this already, but this is like a quadratic. This is a quadratic function. In other words, the sum so far is a quadratic function of the input n. Okay, and you can sort of see this here. Why is it quadratic? Because the constant, the finite differences are giving just the terms of the sequence. And so just, what's this one? This is plus 11, which is to say that the difference between the sum of the first 4 terms and the sum of the first 3 terms is just the 4th term added. The difference between the sum of the first 5 terms and the sum of the first 4 terms is just the 5th term. And so this is now connecting sort of everything we've learned this semester, that if you have a quadratic function, the finite differences are going to be linear. And now this is looking at it from sort of another perspective. If you have finite differences which are linear, then it means that your function is quadratic. Or, another way of putting it is, if you're adding up a bunch of things which are growing linearly, then the formula for that sum is going to be quadratic. And so there's a sort of back and forth kind of relationship between taking sums and taking differences. If you have something which represents a partial sum, then the gaps between the partial sums are just the terms of the sequence. And on the other hand, okay, I'll leave it at that. So what we see here is by analyzing this function, is it sort of just spits out the terms of the sequence. Okay, maybe that's enough already on that problem. Let's kind of finish this homework. So 38 is a very interesting problem, which I have found that a lot of people get wrong by not kind of thinking enough or drawing a picture or something like that. So what is going on? Let's draw a picture. We have this ball which is dropped from a height of 8 meters. Each time it hits the ground, it rebounds 3/4 of the distance it has fallen. That's quite extraordinary. I can't remember the actual physics of, there's like something, coefficient of friction, but I think I can't remember whether this problem is physically plausible or not, but anyway, bouncing to 3/4 the height, that's an extremely small amount of friction. That's incredible if you can get a ball to bounce back to 3/4 of the height. But assuming it does this, and then falls again, and then bounces again, sort of forever, what happens? Well, eventually, the bounces will be so tiny as to be sort of insignificant. Okay, let's make a picture. This is what sort of infinite geometric series are designed for. So we have some kind of picture. What does the picture look like? Well, here's the ball. And of course the ball is understood to be bouncing straight up and down. But if we kind of expand the picture a little bit so we can see what's going on, the ball starts at 8 feet high, and then let's let it bounce kind of sideways or something. So it falls 8 feet. And then it goes back up again. How high does it go? Well, it goes up 6 high, of course. And then it falls. And then it bounces again. How high does it bounce now? Well, it bounces to 3/4 the previous height. And it just does this forever. And each time the height that it bounces is 3/4 as much as the previous one. So this is kind of a nice picture, I think. So it falls 8, but then it goes back up by 8 times 3/4, which is 6. But then it falls again by 8 times 3/4. And then it rises again by 8 times 3/4 squared. Because 3/4 of 6, 3/4 of 8 times 3/4. Okay, so if you didn't draw this picture or think about it carefully, you now sort of realize that what the question is asking, how far does the ball travel? Well, the ball is traveling down and then up and down, up and down, up and down, up and down. So it does every one of these numbers twice, except the first one. So there's a couple different ways of thinking about this. S is just going to be, what I write on my paper, yeah, the first thing it's going to do is it's going to fall 8. Then it's going to rise by 8 times 3/4 and fall by 8 times 3/4 and rise by 8 times 3/4 squared and fall by 8 times 3/4 squared, on and on forever. So now it's just a matter of solving sort of this problem, and maybe the simplest thing to do, what did I do in my paper? Yeah, the simplest thing to do is just write this out, to just do the 8 separately. So this is 8 times, and then, well, I guess this is just 16 times 3/4 plus 16 times 3/4 squared plus 16 times 3/4 cubed, etc. And you're supposed to see that this forms a geometric sequence, that each time we are multiplying by 3/4 because the height that we rebound is 3/4 as much. Okay, and well, if that's true, now I just have to be a little bit careful as I do this. Probably the simplest thing to do maybe is to factor out, I mean there's so many different ways to do this, but you just have to kind of be careful. If you factor out a 16, that's maybe the most natural thing to do. It's actually smoother ways to do this problem, but okay, you can just do this, and then this is an infinite geometric series, so what is this going to be? It's going to be 8 plus 16 times, the first term is 3/4 over, this is a over 1 minus r is the form I'm using right now. So this is a over 1 minus 3/4. And that is going to be 1/4 on the bottom, so that's going to be 3. So this is 8 plus 16 times 3, so that is 56. I think that's the right answer. Now if you got, if you were off by 16, if you got 40, let me make sure I'm doing this right, 30, yeah. If you got the answer of 40, then it means you just totally neglected the fact that the ball's going up and down. You calculated just, if you got 40, then you calculated just the downs, I guess. Hold on, I'm downing myself a little bit, but I think that's probably right. If you got 40, then you calculated just the downs and not also the back ups. In fact, one way to solve this problem is to think of it as 2 different infinite geometric series. One of them is the ups, and one of them is the downs. So the just going down is going to be 8 times 1 plus 3/4 plus, oh yeah, I see, plus 3/4 squared, etc. Cha-cha-cha-cha. And that is going to turn out to be, kind of downing myself now, but I guess that's just 4, so that's just 32. So, is that 4? 1 over 1 minus 3/4 is 4, yeah. So that's just 32. So maybe 32 is the answer that you get if you only compute the downs. But how about the ups? What are the ups gonna give you? Well, the ups, first we go up by 6, and then subsequently it's just more of those. So the ups are going to be 6 times 1 plus 3/4 plus 3/4 squared plus cha-cha-cha-cha-cha. So that's going to be 24, and that's why the total is 56. Yeah. So the first down is 8, and subsequently it's just decreasing by 3/4 every single time. And the ups, the first time up it's 6, and so that's how you get 56. Never mind the thing I was saying about 40. That was just some garbage. All right. Good. Going kind of slowly but thoroughly. Hopefully you're watching on 2 times speed at least. And finish this off. How many terms of the arithmetic sequence 26, 21, 16, etc. must be taken to amount to 74? Okay, so this is a straightforward problem. If this was just a matter of doing this problem as quickly as possible, it would absolutely be fastest to just kind of start adding the numbers. After all, when I add 26 and 21, I get 47. So that's 53, that's 63. I'm really close. So I bet the answer is like, 4 or something. Did I even add those numbers right? 30, 42, it's 63. So is the answer just 4? Yeah, it just must be 4, right? Because the next number, okay. So I already know that the answer is 4 just by duh. Because this sequence is arithmetic, and if the sequence is arithmetic, it's going down by 5 every time. The next term is 11, and I just noticed that if I just add up these 4 numbers, I get 74. Okay, so the goal of this problem is not to just get the answer as fast as possible, it's to employ some kind of systematic method. So what is the systematic method? Well, here D is negative 5, because I'm subtracting 5 each time, and so I have a general formula for the sum of the first n terms of an arithmetic sequence, which is 2a plus n minus 1d, where a is the first term. And so if you tell me that the sum of the first n terms is 74, but I don't know what n is, the way to do this in a systematic manner that's not just like guess and check is to solve for n. So I don't know what n is, but I do know that the first term is 26, so then that's 52, plus n minus 1 times d, in this case, for this problem, is negative 5. And now I have a quadratic equation which I can solve in n. 74 times 2 is 148, yeah? And this is n times, what do I get here? 52 minus 5n plus 5. Okay, so 148 is n times negative 5n plus 57. So what I get is 148 is negative 5n squared plus 57n. And okay, I guess I can solve this. It's 5n squared minus 57n plus 148. Okay, these numbers are kind of big, so you might be thinking, this problem sucks. This is problem number 39, but it must factor. We know it must factor because, assuming the problem is written correctly, n must be an integer. And if n is an integer, which is of course a rational number, then this quadratic has 2 roots. If one of them is rational, the other one is rational as well. So the quadratic must factor, assuming we haven't made any mistakes. So I need to find if I'm doing this problem properly, I need to find the factor pairs of 148. That's almost 150. Well, okay, of course it's 74 times 2, because that's how we got 148 in the first place. 74 is also even, so what is that, 37? And already 37 is prime. So there actually are not as many factor pairs of 148 as you might think. There's, 148 and 1. I hardly think that's going to be the right answer. 74 and 2. And then 37 and 4. That's it. Those are the only options. So actually, factoring this is not so bad. I'm looking for factor pairs which add to 57, and I just find it kind of immediately because 20 and 37. So the factorization here is 5n, 37, and 4, and it's got to be minus minus. This is just algebra 1. So n is 37 fifths or 4, but of course it's not 37 fifths, so it's just 4. Okay, that was page 11. Let's do page 12, which is kind of hard, maybe. Number 40, this is, I don't want to say challenge, but it's not totally obvious what to do. The sum of 3 numbers in an arithmetic sequence is 27. The sum of their squares is 293. Find the 3 numbers. Okay, I think what makes this problem hard for students is there's just they didn't give you the variables, so you have to take your own initiative and you have to sort of say, alright, I have an arithmetic sequence, the sum of 3 of the numbers in an arithmetic sequence is 27, so I just need to have the confidence to sort of pick your own variables. what does a generic arithmetic sequence look like? Well, there's a first term, and then the next term is just d more than that, and the next term is just d more than that. So this is sort of, let's invent letters A and D to represent, the three consecutive terms of this arithmetic sequence. And, there might be other terms that came before this, there might be other terms after, but we're only going to be talking about these three. Okay, well now I have sort of an equation, right? Because what am I being told? I'm told that the sum of these three numbers is 27. So if you add A and A plus D and A plus 2D, then you're supposed to just get 27. Well, that's a very valuable piece of information. And actually, if you clean this up a little bit, that you get 3A plus 3D is 27. I think I did that right, yeah. And dividing by 3, that tells me that A plus D is 9. Okay, so I'm just simply translating the problem into algebra. The sum of three terms in arithmetic is 27. The sum of their squares is 293. So if I square these three numbers and add that, I get 293. Okay, well, I guess I'm just going to do that then, right? A squared plus A plus D squared plus A plus 2D squared is going to be 293. And at this point, I think it's really just algebra because I have sort of two equations in two variables. And even really, if the very first thing you thought to do is to write this equation and this equation, in some ways the thinking is kind of over, and it's just algebra from here, because I write two equations in two variables. So, what is this? It's a squared plus this is a squared plus 2ad plus d squared. This is a squared plus 4ad plus 4d squared, and that is 293. Okay, what do I get here on this left-hand side of the equation? I get 3a squared plus 6ad plus 5d squared? No, 5d squared equals 293. So that's not so nice. And I don't think there's any more. Is this what I did on my paper? Yeah, it is. So I said, it's just so simple because it's a system of two equations, but they're not linear equations. So though intuitively I feel I can solve this, maybe it's just not so kind of clear about sort of what there is to do. But you should feel algebraically that I have two equations, two variables, so I just need to solve this somehow. I guess the thing to do is to just eliminate one variable by doing a substitution. Yeah, that's just it. What I do in my paper, I think there's no particular reason why you should do one or another. We can solve for d. What is d? D is 9 minus a. So if d is 9 minus a, that's what I'm getting from this, then I just stick that in here. So this becomes 3a squared plus 6a. In place of d, I write 9 minus a. And in place of this d, I write 9 minus a squared. And this is 293. Okay, I'm doing this problem in the most kind of boring way. You can actually save a lot of work by doing something a little bit cooler, but I don't know why you would think to do that. So I'll just maybe just finish, because now it really is just algebra 1, right? Solve this quadratic equation. So I guess I just have to do it. Plus, what do we get here? 54a minus 6a squared. Plus, this is 5 times, this is a squared minus 18a plus 81. It's a little harder than I thought. Let's see, these become minus 3a squared, so that's 54a minus 3a squared plus, 5a squared minus 90a plus 245 equals 293. Yeah? And, okay, so this becomes 2a squared minus 36a, that's just right, no, yeah, minus 36a. And then these are 48 apart from each other, so minus 48. Probably doing all this algebra right. Minus 18a minus 24. And what do I get? This is what just happened? Apparently I've made some horrible mistake. 5 times 81 is not 245. Yeah, that's a pretty horrible mistake. 5 times 81 needs some more coffee. 5 times 81 is 405. Good thing I have an answer key here. That was quite bad. Okay, how apart are 405 and 293? They are 112 apart. Okay, there we go. So 56. Do I know two numbers that multiply to be 56 and add to 18? I guess I do. Whoa, 9 times, what? Hold on. What are the products of 56? 28 and 2? 17, 14 and 4? Yeah, there we go. 14 times 4 is 56. So a minus 14, a minus 4. No, I don't even know which one these are. Man, whew. Algebra 1 struggles. So, yeah. And what are we doing? It's going to be a squared plus 4a minus 14a. So there we go. So a is 14 or negative 4. And yeah, it just can't be negative 4. No. Oh my gosh, I made another mistake. This should be positive 112 and positive 56. So these are both negative. And so seemingly I have two different answers to this problem, 14 or 4. Well, if A is 4, then D is 5. And if that's the case, then this arithmetic sequence is in fact 4, 9, 14. But if on the other hand, A is 14, then D must be negative 5. So then this arithmetic sequence is 14, 9, 4. But of course, this is just really the same sequence written in reverse. So we shouldn't. So that's just really there's really just kind of one answer to this problem. Okay, I did say that you could do this problem easier if you were sort of more careful. Or not more careful, if you were sort of smoother, you could achieve this exact same result in far less algebra, but you would have to kind of be experienced enough to think to do that. And that is, if you, instead of writing the generic arithmetic sequence as a plus d, a plus 2d, if you write it as a minus d, a plus d, well then just the numbers just get a lot smaller. So I, after having watched this whole video, if you redo this entire problem just with a slightly different setup, it would seem disingenuous of me to do it this way because maybe you would never think to do this. But now you get some kind of nice things, right? Because when you square these, everything is much smaller now. And when you square these numbers, they sort of match together symmetrically a lot better. And now you're letting a be the middle term. And okay, well, I just promise you, if you redo the exact logic that I just did right here, it's going to be half as much algebra or something like that. Although I'm only remembering this kind of vaguely. Okay, 2 more problems, and then we're going to end this video. And I think they're both pretty chill. Getting very interested in the quality of this whiteboard and how well it erases. Pretty good. 41. The seventh term of a geometric sequence is 192, and the common ratio is 2. Find the first 4 terms. Okay, this is, I think, not so bad. This is 192. We're out here at the 7th term, and the problem asks, what's the first term? Well, to get from the first term to the 7th term, you need to multiply by r 6 times. And so I guess that's it. Oh, and r is 2. They just tell you r is 2. So wait, this is just kind of a silly problem, right? The first term, I don't know what it is, but if you multiply by 2 6 times, then you're just going to get 192. So 2 to the 6 is 64, and so when you divide both sides by 64, you just get that a is 3. That's just it. So what is this sequence? It's the sequence that starts with 3 and then doubles. Okay? 42, I think, is also pretty straightforward. 42 says compute the fourth partial sum of the following geometric series. So this is 2 plus negative a third plus 1/18 plus, okay, so they're telling you that this is geometric, and so you don't have to guess about that. If you look at this, well, what do you have to multiply by? 2 times what is negative a third? I guess I'm multiplying by negative a sixth. And they give you 2 terms so that you can confirm that that's right. Okay, so this is just saying add the first 4 terms. This is another one of those examples where if the goal were just to get the answer as soon as possible, by far the fastest way to do this would be to calculate the 4th term and then just add them all up, just kind of by brute force, but that doesn't indicate any kind of understanding or mathematical technique. So instead we'll use the formula for the sum of the first n terms, which is a times 1 minus r to the n over 1 minus r. And so if I want the sum of the first 4 terms, it's going to be a, the first term, so 2, times 1 minus, you need to be a little bit careful here, that's negative 1/6 to the n, all over 1 minus negative 1/6. And, okay, down here I get 1 plus a 6, so that's 7/6. And this is to the 4. Okay, and here's where, you do have to be, I guess, kind of careful, because this is 1 minus. Is this so gross? Is there just no other way to do this? Yeah, so you're just going to get some huge numbers, I suppose. So this is going to become a positive number, right? This is going to become minus. But when you multiply negative 1/6 times itself, 4 times, you're getting something positive. So this is going to be 1 over 6 to the 4th. I don't think I even know 6 to the 4th. So I'm just going to kind of leave that for the moment. So what do I have here? Let's see. I think the smart thing to do would be to simplify, a little bit. So if you're dividing by 7/6, that's like multiplying by 6/7. So that's going to be 2 times 6 over 7 times, and then this is going to be 6 to the 4th minus 1 over 6 to the 4th. If you sort of see what I did there, this is just kind of advanced fraction manipulation. I got a common denominator inside the brackets, and I middle school flippy this. That's kind of nice because, one of the 6's will cancel, I guess. So this is 2/7 times 6 to the 4th minus 1 over 6 cubed. But at this point I really do need to just do things. Alright, I happen to know that 6 cubed is 216, but I don't know 6 to the 4th by heart. I'm about to tell you what it is. It's 1296. I guess I could have just done that in my head. Because 1296, yeah, so that's not so bad. Alright, so therefore, this is 2/7 times, up top it's going to be 1295, and down low it's going to be 216, and even that can be canceled kind of one more time, so that gives me 1295 over 7 times 108, and I bet 7 goes into 1295, does it? It just totally does, because, well, I just can tell anyway, 5, 9, 8 times 7 is 56, and that's 3, 5, 5. So, yeah, because 15 more 7s would be 105, which would make 1400. So really, the final simplified answer, if you were just, had absolutely no technology with you, and you wanted to do this the hardcore way, this would be 185 over 108 is the final answer to this. Okay, that was pages 9, 10, 11, and 12 of the Sequences in Series packet due today. Goodbye.